So I will start with a short introduction. So imagine that you attend an event where there is a crowd of people watching a performer who is dancing, acting, or maybe doing magic tricks, like in this case. So as you know, and as usually happens, this crowd of people has their own camera with them. And or at least a cell phone with a camera in it, and they record the event. And maybe after that, they share it, maybe on YouTube. As a result, we have a collection of videos of the same event, recorded from different angles. So here in this example, we have only 6 videos, but try to imagine how many videos are recorded, for example, in a concert or a sport event, or an ACM conference, or an ACM party, actually. So the big question here is, given this collection of videos, how does one navigate such a casually captured video collection? And the typical way to do it, and what we are used to in cinema and television, is the classical jump cut, like you see in these videos. But usually in this situation, there is often a director who knows in advance where to place the cameras before the recording starts, and when and where make a cut in practice. However, if you don't have a director, and if you have somebody who doesn't know how to do it properly, the result may get as something that the viewers might get lost and disoriented. So what we propose here is something different. We propose an interactive system to navigate a collection of videos in both space and time, while keeping, during a transition from one video to the other, sense of orientation and surroundings, like in this video. Clearly, this kind of navigation that you saw here is possible only because of a lot of works in both image and video-based rendering. And clearly, our work is, the most closest work to ours is Navely et al. 2006, an extension of which is presented at SIGGRAPH this year, actually. Their system, called also phototourism, does a great job in navigating a collection of images, but it's images. It's only for static environment, and it doesn't deal with moving foreground. Instead, moving foreground was widely studied in both video-based rendering and surface capture communities. And these are only a few examples of them. But most of this work focuses on indoor environments where everything is controlled, from the cameras, which are statics, to the lighting and the background. Some approaches relax this constraint by resorting to a large number of cameras, like in this case. But only few of them have tried to address outdoor scenarios, but mainly resorting to some scene prior, like prior on the environment, like a soccer field, it's a plane, or prior on the dynamic element of the scene, like there is a human in a mock-up system. As everybody knows, in a template motion capture system, if a template is not available for an element of the scene, like in this case, this jacket, its motion cannot be captured. So what else can we do in a casually captured video scenarios, where only few assumptions can be made on the scene, where we have large, uncontrolled environment filmed by non-professional people? How can we perform video-based rendering in such a scenario? So here is the solution that we propose, which is split in 2 main parts, the offline processing and the actual navigation system. I will start by describing you the offline processing, which mainly aims to calibrate the video stream, and segment the main performer. So we bootstrap this process by taking some images of the filming location and by applying structure for motion plus multi-view stereos to obtain a 3D model of all the static elements of the scene. Optionally, at this point, the ground plane is added to the geometry, since it might be missed from the reconstruction. Then, after that, the 3D model is texture mapped. as you can see here. The video collection is then synchronized in time using audio, and each video stream color calibrated with respect to each other and with respect to the texture geometry. The spatial calibration of the video stream is performed by establishing stiff correspondences between the frame to calibrate and the collection of images used in the structure for motion pipeline. Since these images are calibrated with respect to the 3D model, we have a set of 2D to 3D correspondences which can be used to calibrate the camera who took that frame. And by using direct linear transform plus ransack plus refinement. This kind of standard calibration, however, stabilizes only sparse feature point in the image, neglecting the rest. Problems become visible when, like in the video in the center, when we superimpose the original video with the one obtained by rendering the texture geometry at the current camera estimate. So as you can see here in this video, some flicker are visible on the ground. So to recover from this, we took the difference between these two videos and we further optimized the camera pose to minimize such a difference. In this way, we take into account of all the pixels in the image. And this is what we obtain, a more stable calibration with no flicker. Concerning the segmentation of the main performer, everybody knows that segmentation is trivial when a per pixel color model for the background is available. It is when an image of the empty background is available. But in our scenarios, in a casually captured video scenarios, the background is changing because the people are moving in the back and the camera are moving also. This is far beyond the current state of the art for automatic segmentation. And therefore, we asked, in our solution, we asked to a user to manually segment some of the video frame to get the color model for both the foreground and the background. We will need at maximum 2 segmentation per video stream, but this number can really reduce by transferring this color model in between the video stream. After that, we used this color model to perform a color-based segmentation of each input video stream. As you can see here, this segmentation is not able to separate the foreground to the background from the background. But so instead of using it directly as a segmentation, we use it to recover a per pixel color model of the background. And to do that, we extend the approach of Chang et al. 2002 to non-planar geometries to generate camera motion and without the need of any additional user interaction. All this procedure actually is all automatic at this point. Then we use this per pixel color model to improve our segmentation by first applying graph cut and then a simple matting technique, as you can see here. Once all these steps are performed, the video collection is ready to be navigated by our interactive system. I'm going now to describe our system, navigation system actually, and I will start with the user interface. So beside the standard timeline controller, we offer to the user a spatial navigation controller indicating the nearby video stream. Like in this case, there is a video on the left and one behind the observer. A transition to another video stream is triggered by a simple click and drag on the screen. We offer, in addition, another kind of visualization where the performer is marked as a moving sphere and the cameras are shown relative to the pre-computed geometry. What are the concepts behind this visualization tool? So, in a normal video playback mode, everything is simple. The viewpoint of the observer is locked to one of the cameras of the video collection. Once the user requests for a transition, for example to camera 2, the system needs to be able to generate all the intermediate views along the transition path. And we perform this by modeling the background using the pre-computed background geometry and by modeling the foreground instead using billboards. Concerning the background, since the colors of the pre-computed texture might not be consistent with the video stream, like in this case, the shadows are missing in the pre-computed texture, we choose to adapt Unstructured LumiGraph, which use, when it's possible, the color from the video stream, and we adapt it to moving cameras to mask out the foreground, and we limit this approach to only 3 sources to maintain real-time performances. Concerning the foreground instead, probably you're asking yourself, why are we still using simple billboard to model it? What about using shape from silhouette or dense stereo to get a more complete 3D model of the performer, of the foreground? So we apply shape from silhouette on this chainsaw juggler sequence, the one that you saw before, and this is what we obtain. Shape from silhouette is too sensitive to calibration and segmentation error, because in practice, basically, it's an end operator, and even a small error in only one of the video stream corrupts the entire reconstruction and affects all the transition at that moment. Dense stereo instead needs dense camera arrangement, which is not guaranteed to have in a casually captured video scenario. Like in this case, the 2 cameras are too far apart, are very far apart. Therefore, we resort to billboards, which are more robust, but they have their own drawback, which everybody knows, and which actually is visible during a transition at the moment of the billboard switch. If you can see it here, just look at the arm of the performer. At that moment, in the middle of the transition, there is an annoying artifact, which is due to the fact that at that point, the 2 billboards represent 2 different sides of the performer. To recover from these artifacts, instead of transitioning right after the user request for a transition, in our solution, the system waits and actively searches in parallel to the video playback for the best moment to make the transition. And this is what it found. As you can see here, the billboard switch is hidden inside the motion of the performer. So, how we evaluate the best moment to make the transition? So we use what we call inter-billboard distance, which in practice is a distance transform between the 2 silhouettes viewed by the performer, by the observer at the moment of the switch. So if there is an agreement between these 2 silhouettes, then the distance is small, and that is a good moment to make a transition. On the contrary, if the distance is high, that is a bad moment to make a transition. This has also the extra benefit of taking into account for segmentation and calibration error, because in that case, the distance will be higher, and so the transition will be avoided automatically by the system. If you're still not convinced, I show you a side-by-side comparison between unoptimized and optimized transition. Obviously, the optimized ones are a little bit delayed from the unoptimized one. As you can see here, we take into account of segmentation error in the optimized transition, like here, that was visible. Okay. We offer to the user 3 different transition styles. The first one is the dot transition, clearly inspired by phototourism, where the background is rendered as a point cloud. The second one is the blurred transition, where only the foreground remains sharp and the background is motion blurred. And then finally, the in-focus transition, where the entire image during a transition remains sharp. So before leaving you to the final result, I would like to draw the conclusion. We present an interactive system to navigate a collection of videos which was able to perform video-based rendering in an uncontrolled outdoor scenarios. We explain you how we calibrate the video stream using all the pixels in the image. We explain how we segment the main performer, exploiting the information of the static element of the scene. And we explain you how we optimize the transition to work around the limitation of the billboards and to recover from possible error of the first two steps, the segmentation and the calibration. In the paper, you will find details about the camera path interpolation, which is particular for this case, and also details about the user study that we ran to evaluate the usefulness of our system. Two are the main limitations, actually. The first one is the availability of the data. In most of the video that you saw before, we collected ourselves, because since even if YouTube or other video sharing service has a lot of videos, they don't represent the same event. They don't overlap in space and time. The second main limitation is that our system is performer-centric. It assumes that there is a performer in the scene. If there is other people in the scene, it will try to model them as a billboard too. But if there are too many and it cannot distinguish between the videos, it will fail, like in this case. So you will find more results in our webpage, but here I want to show you the most challenging input footage video-based rendering has ever been applied to so far. And it includes also a 100 degrees transition, which you might notice it. So enjoy it.
Okay, folks, watch this, guys. First of all, a quick warm-up with one chainsaw, then a 3 chainsaw finale. Can everybody help me out? The people in the front, can you sit down for the last 2 minutes so everybody at the back can see? Just the guys at the front so everybody at the back can see the last 2 minutes. Thank you very much.
Oh, yeah, he's about to cut an apple or something, a ball or something in half, I think. And he's going to do something with flame, and it's all going to be very
exciting. Check the blade, people, check the blade.
I gotta go, yeah?
Check the blade, folks. Okay, guys, get ready to clap, please. Get ready. After this. And I thank you all personally for watching the show. Thank you very much. Thank you.
And thanks to all of you.
Thank you.
We have time for some questions. Can you please come up to the microphones? Go ahead.
Hi, so I'm just curious with this photo tourism and video tourism stuff, if you did go online and try and find multiple videos of the same scene and try out using your software on that sort of thing.
Yeah, I would like to have done this. So the problem is that, like I said before, we try to look on YouTube and there is not so much footage of the same event. They don't overlap in space and time. Actually, Gable observed me that the only one multi-camera footage was actually, I think, Madonna kissing another girl. So I think we are not interested in that. So I think in the future there will be. For the moment, yeah, we had to collect our footage ourselves.
I see. So for the moment, the application is more like video you take when you plan to do something like this, so you're not really taking advantage of the photo tourism aspect yet?
I didn't understand the question.
So what's the application for the moment?
So the application for the moment, you can see it in this way. The only one problem is collecting the video. So we need somebody who share it. I mean, this is what we did. So we asked to some guys to go there to the event, record it, and then give us the videos. So in that case, it's applicable in that scenario. So you can think if you have a group of friends that go to an event and then record it, then you can navigate it. Yes, in that case, yes. Or a concert, for example, that would be ideal, right? Yeah.
Thank you for that question. Are there other questions?
Yeah, hello. Mark Haller from HI Corporation.
Hi.
You mentioned just in passing that you used the audio to synchronize the different videos. That seems like quite a challenge in itself, because there must be quite significant differences in the audio from the different cameras.
Yes.
Can you comment on that briefly?
Yeah, sure. I mean, the audio is one possibility to calibrate the videos. And we choose to use that because it was simple. But obviously, if you have cameras that are pretty far away, maybe one is, probably in this case will be no problem. But if the camera, if the video stream doesn't share the same audio, you cannot calibrate. But in that case, you can use other technique, which like visual technique that try to infer the synchronization by looking at the images, and that could be a solution.
I'm afraid we've run out of time for questions. I see there are two other people. Please come up to talk to the speaker after the session's over. So let's thank our speaker once again.
Thank you.